Welcome to this explainer. Let's kick things off right out of the gate with a pretty radical question. What if your idle, everyday devices, the ones gathering dust in your closet right now, could actually run massive, state-of-the-art language models like ChatGPT entirely locally?
Well, today we're going to demystify distributed AI inference. We'll show you exactly how to combine your old, disjointed hardware into a highly capable, entirely private AI supercomputer right in your own home. Okay, here's our architectural blueprint for today. We'll be looking at 1. The giant LLM problem. 2. The local AI mesh network. 3. Pipeline versus tensor parallelism. 4. Thunderbolt and Ethernet networks. 5. EXO, Prima, and smolcluster. And finally, putting together your home AI supercomputer.
So let's jump right into part 1, the giant LLM problem, and specifically why a single GPU just isn't going to cut it.
We really have to start with the fundamental bottleneck that's preventing you from running frontier models locally. And that's memory capacity. Look, a 70 billion parameter model running in FP16 precision requires a staggering 140 gigabytes of memory just to hold the weights. To put that into perspective, an enterprise-grade NVIDIA H100 only has 80 gigabytes. So a 70 billion parameter model completely eclipses the capacity of standard consumer GPUs. You'd need multiple, insanely expensive cards just to load the model, let alone actually process a conversation.
Which brings us to section 2, the local AI mesh network, and how we go about pooling your underutilized resources. The crucial point here is how we solve this massive memory limitation. Because instead of renting out enterprise data centers or buying a ridiculously expensive server, you can actually Frankenstein a local AI mesh network. You do this by linking together heterogeneous hardware, meaning devices with completely different architectures. We're talking about pooling the unified memory of Apple Silicon Mac Minis, the VRAM of legacy GPU mining rigs like the Tesla V100, the RAM from single-board computers like Raspberry Pis or NVIDIA Jetsons, and astonishingly, you can even tap into the neural engine of that dusty old iPad you have lying around. No joke.
Moving on to section 3, pipeline versus tensor parallelism. This is all about how we actually split the artificial brain. To make all these vastly different devices act as one cohesive brain, we have to split the mathematical workload using parallelism. And the contrast between the two main approaches here is absolutely fascinating. On the left, we have tensor parallelism. This splits the matrix math inside each individual layer. This means every GPU has to compute simultaneously. They're acting like a synchronized team, instantly solving fractions of a single equation together. On the right, pipeline parallelism splits the model sequentially by its layers. So GPU 1 handles layers 1 through 10, passes the result to GPU 2, which then handles 11 through 20. It acts exactly like an assembly line passing a baton. But here's where the physical reality of your home network totally dictates your software choices. Because tensor parallelism synchronizes constantly, literally multiple times per layer, it demands over 100 gigabits per second of bandwidth and microsecond latency. Try doing that over Wi-Fi, and well, the time spent waiting for network packets will be orders of magnitude longer than the actual computation. Pipeline parallelism, however, only synchronizes at the stage boundaries. It only requires around 1 gigabit per second of bandwidth. That makes pipeline parallelism the clear, resilient winner for scrappy home labs running on standard Gigabit Ethernet.
Let's move over to section 4, Thunderbolts and Ethernet networks. Let's see how we build this hybrid physical layer.
If you want to link highly diverse hardware without your slowest device completely bottlenecking the entire system, you need a tiered hybrid physical topology. First up, you build a high-speed backbone. For example, connecting Apple Silicon Mac Minis using Thunderbolt cables on a dedicated subnet that gives you 20 to 40 gigabits per second. Next, you build the edge, connecting your lower power boards like Raspberry Pis via standard Gigabit Ethernet to a secondary interface on one of those Macs. Finally, you enable IP forwarding on that gateway Mac. This ensures your edge devices can communicate across the network without forcing that ultra-fast Thunderbolt backbone to slow down to Ethernet speeds. It's a brilliant workaround.
Now we arrive at section 5, EXO, Prima, and smolcluster. This is the software orchestration layer that actually makes all of this happen.
First up is EXO, and honestly, this open source framework behaves almost like magic. It features automatic peer-to-peer device discovery, meaning your devices just find each other on your network without any manual IP configuration.
It dynamically partitions the model shards based on the memory capacity of each device. And while it was originally focused on Apple Silicon using the MLX framework, there's a brilliant fork called ExoCUDA that restores full NVIDIA support. So yes, you can mix Macs with old Tesla V100s, and the best part, it exposes a local ChatGPT-compatible API so you can literally plug it straight into your existing apps.
Next up, we have smolcluster. This is a brilliant educational library built from the ground up using raw Python sockets, explicitly avoiding high-level networking frameworks. Why? Well, so you can actually understand how the communication, synchronization, and scaling behavior work under the hood. It features zero config node discovery via a tool called Grove, and it actually teaches you how distributed training algorithms function. It is incredibly versatile. In fact, its architecture is perfectly suited for running hybrid inference, like splitting a model's layers between a Mac Mini and the Core ML engine on an iPad.
Which brings us to our third software highlight, and a massive breakthrough, prima.cpp. This framework uses a strategy called piped ring parallelism. Basically, it passes data through your devices arranged in a logical ring, but its real superpower is that it aggressively prefetches upcoming model weights. This allows it to overlap the heavy computation with the disk loading. By doing this, it completely hides the latency of reading from slow consumer hard drives. It makes massive models run fast, even on cheap, low-resource laptops that lack sufficient RAM. Now, while EXO does a fantastic job of splitting the model primarily based on available memory, prima.cpp actually goes a significant step further. It utilizes what's called the Halda scheduler. This algorithm uses linear optimization to dynamically profile your specific cluster's unique quirks. It's analyzing CPU power, disk read speeds, RAM, and even how different operating systems manage memory. By doing this, it assigns workloads so perfectly that it keeps memory pressure on your individual devices below 6%. That is absolutely crucial for entirely preventing those frustrating out-of-memory crashes. All right, we've successfully navigated the architectural blueprint. Let's move to our final section, your home AI supercomputer, and putting it all together.
We've gone from the staggering memory requirements of giant LLMs down through the hybrid networking of Thunderbolt and Ethernet and into revolutionary software frameworks like EXO, smolcluster, and prima.cpp. And this developer quote from our source material perfectly captures the empowering reality of this entire movement, unifying all local, unutilized compute available nearby you. You literally have the ability to repurpose the obsolete tech sitting in your closet right now to build a fully private, highly capable distributed inference cluster. The enterprise tech giants want you to think you need their billion-dollar data centers to play in the space. But now that you have the blueprint, what will you build with your own private, decentralized AI supercomputer? Thanks for joining me on this explainer. Now seriously, go raid your closet.